Welcome to the last topic of the second half of the course. This is an extension to the previous displacement formulation that we have looked at. And in displacement formulation, I mean the complex variable displacement potentials. Okay, and we have seen one example where we have solved the two-dimensional version of a Kelvin problem. Now, we will just extend the same formulation to problems which are say inhomogeneous, rather where the objects are inhomogeneous. Okay, so let me try to first give you a glimpse of what we have sort of assumed or what went behind our mind, which is the following. uh, Previously or till now we have solved problems where the domain was simply connected. Okay, we have seen in when we derived the strain compatibility equations what we meant by simply connected, right? And we further assumed that these are all homogeneous, right? Everywhere it is, if it was steel here, it is steel everywhere. Okay, so these were two things that we sort of assumed in all the problems which we have solved over the last 14-15 lectures. Okay, the domain was simply connected, or in fact it was simply connected for us, and the material distribution was all homogeneous, right? And further we have solved this for isotropic problems only, or isotropic materials only, right? We have not solved anything for anisotropic materials. Now there are class of materials where, or equal class of structures. Say for example, if you have previously solved the case for a plate, right? We have assumed that the plate was homogeneous spatially and it was isotropic. Often you do end up with problems where where your material is probably drilled with a hole or maybe multiple holes, right? And this is all the material. You just that it is now simply, it is not simply connected. It has couple of inhomogeneities, and an unwanted inhomogeneity could be something like you have a crack or maybe you have few cracks. Okay, so mathematically speaking they are inhomogeneous. That's first. Inhomogeneous, why? Because first was the original material, now you have this vacuum or air regions, or in the first case it is the circular holes or whatever shaped holes they are. Okay, now there are basically two materials, one was our original material and second is air or vacuum. So that is the reason it is spatially inhomogeneous. Okay, we are still assuming one thing, we are still assuming that it is isotropic, as in this direct properties in this direction and this direction, in any direction in the two-dimensional plane the properties remain constant. Okay, that is what we are assuming. So these are inhomogeneous materials. Inhomogeneous. Okay, so we will see how we can extend the complex displacement formulation to the inhomogeneous materials. Okay, all further we will bank on one concept which we have already learned, and it was already given in the handout, is the Taylor series, or the sorry, the power series expansion. Whenever the, and the other thing which we have seen is uh, for an analytic function, say y of z, and z is a complex or it could be just purely a real number. If the function y is, if this is y is confusing, let's switch to f, because y and z normally both of them represent the spatial variables. If a function f and whose variable is z, where z is complex or real quantity, if it is analytic, then at z is equals to 0, if the function f is analytic at z is equals to z0, then I can write it locally. I can expand this function as a power series formulation, right? Z minus z0 or n, and running from 0 to infinity, right? This is what we have said. Now when there are singularities, what people have come up with is saying you can still expand your function so long as it is a, it can be convertible to a analytic function, instead of n running from 0, it will run from minus infinity to plus infinity. And that is how you're going to deal with the singularities. All right. So with this foundation of mathematics, we will go to the next. We will go ahead and solve the remaining, rather this problem. Okay. Uh, Complex for potentials which falls in displacement formulation. All we are saying is you have two components of displacement u and v, and you're creating a complex number such that uh, it encompasses both the components of displacement, right? And we have seen in terms of the complex displacement potentials how the displacement vector or the complex displacement can be written in terms of the potentials and with a particular factor kappa, which can be tuned for plane stress and plane strain problems. And then we were able to write the stresses in various forms. Further, we have solved one such problem, and where we have also looked at the traction boundary conditions. So basically, in a complex potential displacement formulation, you choose two potentials, psi and omega, or psi and w, and you already have the displacement written in terms of these potentials. And once you know displacements, that is how we have identified various forms of writing the stresses, right? And we have also tried to write the boundary condition in terms of the potentials, right? This is all there was to it. Right? Complex potential formulation comes in a nicely fed manner, just that we need to choose the functions wisely. Okay, how does that wisdom come? It comes mainly through practice. Okay, so this is what we have seen so far. Now the only addition which we will make is the following. Right? You are expanding in terms of Laurent series, and wherever there are singular points. What were singular points with respect to the examples that we have, which I have discussed on slide number 1? The singular points were the regions where the holes were drilled or where the crack was placed. For example, I'll give you one more singular point which most of you must have come across. Let's say this is a stream where there is water flowing. Okay, it's continuously flowing from left hand side to the right hand side. Now, when there is no stone, no plant, no log in it, no wooden piece in it, it'll smoothly flow. However, if I put a stone, if I put a big enough stone, what will happen? The flow will go around it, right? Whereas the velocity of the flow at the point where there is the stone is zero. Velocity is where the flow is stagnant at the point where there is the presence of stone. So that particular point is called as singular point. Likewise, for us, the singular points are the regions where there is inhomogeneity. The inhomogeneity can be a crack, a hole, or a different material itself. All right. So all we are saying is, let me define those my singular points be with some zk. Okay, and I can have many such. K is representing basically the number. K is equal to 1, 2, 3, 4, 5, 6, so on, is basically representing the inhomogeneity number. And I am also saying let that force on that be a complex, sorry, let that force vector be xk I hat plus yk j hat, which basically in our complex formulation can be written as xk plus I times yk. This I is again square root of minus 1. So this is how the general form, this is the suggested general form of the complex potential that we take. Let us examine. Our previous formulation was simply ak z minus, an times z minus z0 whole power n, and it was a summation over n. That was the general form for psi. Now, for every inhomogeneity k, I am having a particular kind of a. Further, I have one additional term which is coming in the form of this. Wherever there is singularity, I am instead of 1 by z, instead of simply log z, I have a term logarithm of z minus zk. Okay, and these are just the additional terms. Okay, whatever previous form you choose for a plate without holes, you have those potentials plus this additional term. Okay, so this is that additional term which is taking care of the forces and all. Okay, so likewise you choose for the W. If you notice, the difference is there you have plus in psi of z, you have xk plus I times yk, whereas for omega or W, you choose xk minus I times yk. That's the difference in the form. Otherwise, rest of the terms remain the same. Okay, and in the presence of far field stresses, you end up adding one more term. This is what I was saying. These first two expressions, the general forms, are for without any far field stresses. They are just accounting for the local variation. As in, there is in case one, you have a plate without holes, and due to your boundary conditions and body forces, there is say a set of stress and strain states on it. Okay, and you for those stress and strain states, you do end up having a particular pair of complex potentials. Now, whatever is listed as these general potentials, psi z and w of z, with these two long terms, these account for just the changes that occur in these potentials due to the existence of inhomogeneity or due to these singular points. Okay, and that is the reason when you have far field stresses, you need to account for this additional term for both psi and w. The last term is what is actually being accounted for. All right, so with respect to theory, this is all there is to it. So let us go ahead and solve one particular problem. Okay, I am taking an infinite plate with a hole uh, at radius a, and the center of that hole is at the origin, and it is subjected to far field stresses which are leading to stresses sigma xx0, yy0 and xy0. As in, you had a plate when there was no inhomogeneity, you had stresses in it which were sigma xx0, sigma yy0 and sigma xy0. And I am assuming one more thing, that these stresses are constant with space. Okay, you had a plate, no inhomogeneities in it. However, you somehow ended up inducing or developing a state of stress given by these sigma xx0, yy0 and xy0. And now you are having a hole in it whose center is at A, whose center is at the origin, and the radius of that hole is A. We have to find out what is the stress distribution when you have this such a kind of scenario. Okay, and I'm assuming a plane strain condition now that there are no body forces. There are no. We are right now. I'm assuming a plane strain condition. These are my domain equations. Right. I'm dealing with complex in the polar form mainly because the shape of the inhomogeneity is in a circular shape. No other particular reason. Okay. I have chosen to write sigma rr and sigma theta theta. And likewise, you can get the other expressions. I'm not, or you can always refer back to your lecture number 15 to get these expressions, or you can derive it or refer to the book by England, Complex Variables in Theory of Elasticity or Complex Variables in Elasticity. Okay, so these are the domain equations, right? And the traction boundary conditions. There is only one boundary, which is the interface of the hole and the infinite plate. That circle which you see in the figure is the only inhomogeneity, is the only boundary. Right? At r is equals to a, right now the traction is 0. Right? If that region was pressurized, then you'll have to say that this traction is equals to minus p. Right? Something which you all must be used to now. So at the minute, simpler problem. So I'm trying to say that the traction is 0, which means I can end up getting a equation in terms of the complex potentials. At r is equals to 0, this expression should vanish. All right, and I am choosing the following form of the potential. Okay, and same thing for W. Why did I not choose the logarithmic term? Because in I think slide number 3, I have said that there were two sets of terms. One was this an term, and the second one was the first term xk plus I times yk times logarithm of z minus z0, z minus zk. Right? When did we say that the first term will come into existence? When you had your body forces. Right now there is no body force, or rather not body force. The force acting on the singular point was xk plus I times yk. Right now there is no force there. Okay, so that is the reason I have not chosen it. Further, in the general form, I have written a and k, and k was the number of singular points, summation or the number of singular points. Since I had only one singular point, instead of writing it as a n 1, I am simply writing it as a n. Likewise with bn. Okay, and the second terms in these expressions, second terms as in these two terms, are accounting for the far field variation. Okay, far field as in at regions away from the inhomogeneity. Rather, our inhomogeneity here is a small circular hole of radius a. So this term which is circled in here is will account for the stresses which are far away from the circular region. Okay, so let's proceed. So these are the general expressions, and I'm going to substitute it in the boundary condition. Okay, I have substituted it in the equation last equation of slide number 4. I have substituted the general form, which is a general form as in the chosen form for this problem for psi and W. I'm substituting this in the last equation of slide number 4, which is the fraction boundary condition. That is the only condition which we have. Okay, nothing else is there. There is no displacement condition. All right, so I'm substituting the chosen form of potentials in the domain equation, in the governing equation. The governing equation for us right now is only the boundary condition. Okay, I'm substituting it and I'm sort of expanding them for different terms. N is equals to 1, n is equals to 2, n is equals to 3, and n is equals to 4. The last term, this particular term is for n greater than or equal to 4. Okay, and I'm comparing the left hand side and the right hand side. Okay, I am only seeing exponential 2i theta terms here, whereas I on the left hand side I am on the right hand side I am seeing various kinds of terms, exponential 2i theta minus 3i theta, all these terms, but each one of them is being accompanied by one such coefficients. So I'm going to equate rather the like terms of exponential in the exponential terms. Okay, I'm going to equate the exponential I theta on the left hand side term to the exponential I theta on the right hand side. Likewise, I'm going to equate every exponential term on the left hand side with its corresponding right hand side term. Okay, so that's what I have written here. Comparing the coefficient of exponential terms, I would get the following: that an only the a1 has a finite value, non-zero value, and b1 also has a non-zero value. Remaining all terms vanish. So once you know an and bn, so b1 and b3 are non-zero, and the remaining terms are all zero. So once you know this ai and bi, you can identify the we can identify the stresses. Okay, I only wanted to demonstrate the concept. Okay, the concept on using how do we use this Laurent series. Okay, well, I've stopped at this point where we have where I evaluate the displacement, where I evaluate the coefficients. Because what is the logical sequence of steps? Once I know the displacement, once I know these coefficients, I can identify psi z and omega of z. Once I know psi z and omega of z, I can identify displacements. And in tandem, I can identify the stresses because I already know the expressions in for stresses in terms of the potential functions. And either using displacements or using the stresses, you can identify the strain fields. Okay, so this is it with respect to the concept of Laurent series, and in particular with respect to complex potentials. The list of topics in theory of elasticity is uh, especially in this course is not completely exhaustive. We can go on for another 40 lectures in discussing various kinds of techniques. However, please note that we have equipped you with enough number of techniques now in terms of airy stress function as well as displacement formulation. In airy stress function, you have seen few kinds. What are they? First is the polar form of solution, then Cartesian form, and in Cartesian you have also seen the Fourier series. When I say Cartesian, you first saw the polynomial form of solution, general solution. Then you have seen the Fourier series, right? And then there we have seen both plane stress and plane strain problems. Then we have seen how to account for the body first force terms, and so on. Likewise, in displacement formulation, we have seen starting with Helmholtz potentials, and then we have seen Popkovich-Neubel potentials, and then we have seen Bose-Einstein problem. We have solved the Bose-Einstein problem, and then we have come to the complex displacement potential. And before doing that, we have also seen how one kind of displacement potential, such as Helmholtz potential, can be related to Popkovich-Neubel potential. And once you know these two, you can relate it to the Law's strain potential or Lamè's strain function, and so on. Okay, so one set of potentials are always related to the other set of potentials. So that is what we have equipped you in this course. Towards the end of this course, this is what I have aimed to uncover, that you will be equipped with a set of formalisms in solving uh, most commonly occurring problems like the dam, a door, okay, a table kind of problems. And that is what we have managed to accomplish so far in this particular series. So, like I said, the the set of techniques are not just confined to this course. Okay, depending upon what your research takes you in, you may end up looking at more number of techniques, or you may end up developing some technique on your own. Okay, so please make notes, and I will probably meet you in the discussion session. Okay, thank you so much.